Welcome to Dreamy Science, where we explore the fascinating world of scientific wonder. Here's something that should keep you up at night, but probably won't. Right now, as you're listening, you're not truly touching anything. Not the bed beneath you, not the air around you, not even your own skin. Every interaction you perceive as touch is, at its most fundamental level, an illusion, a repulsion of electromagnetic fields. Your hand doesn't actually make physical contact with the wall when you push against it. Instead, the electrons in your hand generate an electromagnetic force that pushes back against the electromagnetic force generated by electrons in the wall. It's like trying to push two powerful magnets together at their repelling poles. You feel resistance, a sense of solidity, but the magnets themselves never actually touch. They're held apart by an invisible force field. And this isn't just a metaphor for how things feel at the subatomic level. This is literally what is happening. Your entire experience of the material world, everything you perceive as solid and tangible, is a symphony of invisible forces playing out in a vast, mostly empty space. The chair you're sitting on, the floor beneath your feet, the very atoms that make up your body, all of it is an incredible dance of energy and force with very little actual stuff involved. It's a profound realization that shatters our common sense understanding of reality, suggesting that the universe is far more ethereal and strangely interconnected than we could ever imagine. If you're enjoying this journey through the fascinating world of science, I'd love it if you'd hit that like button and subscribe to Dreamy Science so you don't miss future episodes. And I'm always curious. Drop a comment letting me know what city you're watching from and what time it is where you are. There's something special about knowing this exploration of scientific wonder is reaching people all over the world at all hours of the day and night. Let's begin with a mind-bending truth. The very solidity you perceive in the world around you and even within your own body is an illusion. It's an illusion so profound and so deeply ingrained in our everyday experience that it takes a fundamental shift in perspective to truly grasp it. When you lean against a wall or hold a book, or even just wiggle your toes, you feel a distinct sensation of resistance and contact. But at the most fundamental level, the particles that make up your body are never actually touching the particles of the wall, the book, or even your own toes. Instead, what you're experiencing is a powerful electromagnetic repulsion that mimics the sensation of physical contact. You are, in essence, a ghost interacting with a world of other ghosts, all held apart by invisible force fields. To understand this, we need to zoom in, way in, to the very building blocks of matter, atoms. Everyone knows atoms are small, but this word small doesn't quite capture the scale of emptiness we're talking about. Imagine a hydrogen atom, the simplest atom consisting of a single proton in its nucleus and a single electron whizzing around it. If we were to scale up that proton to the size of a marble, the electron would be a tiny speck, far smaller than a grain of sand, orbiting at a distance of about 1 kilometre. That's over half a mile away. So if the nucleus is a marble, the electron is a speck orbiting 1 kilometre away, and everything in between is nothing, just empty space. Now let's apply this to something more tangible, like your own body. Your body is made up of trillions of atoms, and if each of those atoms is mostly empty space, then it logically follows that you are mostly empty space. To put it another way, if you were to compress all the protons, neutrons and electrons that make up your entire body, removing all the empty space between them, your entire physical form would shrink down to a volume smaller than a grain of salt. Yes, your entire being, weighing exactly the same, would fit into a speck of matter too tiny to see with the naked eye. This incredible density, this fundamental stuff of you, is concentrated in an unimaginably small volume. The vast majority of what you perceive as you is, in fact, the empty space within your atoms. This concept of atoms being mostly empty space isn't new. It was dramatically revealed by Ernest Rutherford's famous gold foil experiment in 1911. Before Rutherford, scientists generally believed in the plum pudding model of the atom, where positive charge was spread out like pudding with electrons embedded within it, like plums. Rutherford, along with his students Hans Geiger and Ernest Marsden, fired a beam of positively charged alpha particles at a thin sheet of gold foil. According to the plum pudding model, these alpha particles, being relatively heavy and fast, should have passed straight through the foil with only minor deflections. But that's not what happened. While most alpha particles did pass straight through, a small percentage were deflected at very large angles, and an even smaller percentage, about 1 in 8,000, bounced back almost directly at the source. It was, as Rutherford famously put it, almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. This observation was revolutionary. It meant the positive charge and most of the mass of the atom couldn't be spread out. It had to be concentrated in a tiny dense core, the nucleus. The alpha particles that bounced back had directly hit these incredibly small dense nuclei. The vast majority of the alpha particles passed straight through simply because they were travelling through the immense empty space between the nuclei and the orbiting electrons. This experiment fundamentally changed our understanding of the atom, revealing its surprisingly hollow nature and setting the stage for quantum mechanics. It showed us that matter is not solid in the way our common sense tells us. It is instead a diffuse cloud of probability surrounding a tiny, dense core. So if atoms are mostly empty space, why does a wall feel solid? Why don't we simply pass through each other like ghosts? This is where the electromagnetic force comes in, and it's where quantum physics really starts to dismantle our common sense notions. The solidity we perceive isn't about physical contact in the way we usually think about it. It's about forces. Specifically, it's about the electromagnetic force, which governs how charged particles interact. The electrons in the outermost shells or orbitals of the atoms in your hand are negatively charged. The electrons in the outermost shells of the atoms in the wall are also negatively charged. And as we know, like charges repel. When you push your hand against the wall, the electron clouds of your atoms get closer and closer to the electron clouds of the wall's atoms. As they approach, the electromagnetic repulsion between these negatively charged electrons becomes incredibly strong. This repulsion acts like an invisible springy cushion, pushing back against your hand. The harder you push, the stronger the repulsive force becomes, preventing the electron clouds from interpenetrating. It's this powerful short-range electromagnetic force that gives matter its apparent solidity and resistance. You're not actually making contact with the wall, you're just experiencing the force field generated by its electrons pushing back against the force field generated by your electrons. But there's an even deeper, more fundamentally quantum reason why atoms don't collapse into each other, and why matter occupies space so effectively, despite being mostly empty. This is the Pauli exclusion principle, a cornerstone of quantum mechanics discovered by Wolfgang Pauli in 1925. It's one of those principles that doesn't have an easy classical analogy because it describes a purely quantum phenomenon. The Pauli exclusion principle states that no two identical fermions, and electrons are fermions, can occupy the exact same quantum state within an atom. What does quantum state mean? It's a precise description of an electron's properties, including its energy level, its orbital shape, and its spin. Think of it like a unique address with specific characteristics. The Pauli exclusion principle essentially says that electrons are fiercely individualistic. They refuse to share the same address. This principle is why electrons don't all just pile into the lowest possible energy level around the nucleus. Instead, they fill up distinct energy shells, each with a limited number of slots for electrons with specific quantum properties. Each electron needs its own unique set of quantum numbers, its own unique address. This has profound implications for the solidity of matter. When you try to push two atoms together, their electron clouds begin to overlap. For the electrons in one atom to occupy the same space as the electrons in another atom, they would have to occupy the same quantum states. But the Pauli exclusion principle forbids this. It's like trying to fit two people into the exact same chair at the exact same time. It's simply not allowed by the fundamental rules of the universe for these particular particles. This quantum repulsion is what gives atoms their distinct size and prevents them from interpenetrating. It's not just the classical electromagnetic repulsion of like charges, it's a more fundamental quantum mechanical resistance to sharing the same space in the same way. It's a pressure, a degeneracy pressure, that arises purely from the quantum nature of electrons. So the solidity of matter is a multi-layered illusion. First, atoms are mostly empty space. Second, the apparent contact we feel is due to the electromagnetic repulsion between electron clouds. And third, and perhaps most fundamentally, the Pauli exclusion principle prevents electrons from occupying the same quantum states, thereby giving atoms their distinct boundaries and preventing macroscopic objects from simply passing through each other. This principle is so powerful that it's what prevents white dwarf stars from collapsing further under their own immense gravity, holding them up against the crushing force of their own mass. It's a cosmic scale manifestation of the same force that makes your desk feel solid. This understanding of matter fundamentally alters our perception of reality. The world isn't a collection of tiny, hard, billiard ball-like particles as classical physics once envisioned. Instead, it's an intricate dance of fields and probabilities where solidity is an emergent property arising from the interactions of quantum particles that are themselves mostly empty space. When you touch something, you're not encountering a physical barrier of solid particles. You're encountering the powerful, invisible force fields generated by the electrons on the surface of that object, which are prevented from interpenetrating by the fundamental rules of quantum mechanics. It's a universe of ghosts and forces, not of tangible stuff in the classical sense. This revelation has profound implications for how we think about everything from the structure of materials to the nature of consciousness. If our bodies are mostly empty space, and our interactions are mediated by invisible forces, then our common sense notions of physical and material begin to dissolve. It invites us to consider a reality where information, fields and interactions are more fundamental than the seemingly solid objects we perceive. This isn't just an abstract scientific concept, it's the underlying reality of every single interaction, every sensation, every moment of your existence. This journey into the emptiness of matter is just the beginning of how quantum physics challenges our everyday understanding. We've seen that the stuff of the universe is far less substantial than we imagined, and that fundamental quantum rules like the Pauli exclusion principle are responsible for the very existence of solid objects. But what about the particles themselves? If electrons aren't tiny planets orbiting a nucleus, what are they? How do they behave when they're not interacting with other particles? And how can something be both a particle and a wave at the same time? These questions lead us into the heart of quantum weirdness, where the very nature of reality becomes even more elusive and fascinating. Next, we'll explore the bizarre concept of wave-particle duality, and discover that the fundamental constituents of the universe don't just defy our sense of touch, but also our sense of identity. Welcome back to Dreamy Science, where we continue our journey into the mind-bending truths of quantum physics, truths that systematically dismantle our everyday notions of reality. Last time we shattered the illusion of touch and discovered that the solid world around us, and even our own bodies, is mostly empty space, held apart by invisible forces and the peculiar rules of the quantum realm. We learned that the very concept of solidity is a multi-layered illusion, an intricate dance of electromagnetic repulsion and the Pauli exclusion principle. But what about the particles themselves? If they aren't tiny, hard spheres like miniature planets or billiard balls, what are they? And how do they behave when they're not interacting, when they're just existing? This is where quantum mechanics doesn't just bend common sense, it utterly obliterates it, replacing it with something far more wondrous and profoundly strange. Imagine, if you will, the most fundamental constituents of reality: electrons, photons, quarks. Our common sense, steeped in a world of tangible objects, wants to picture them as tiny, definite points, like speckles of dust, each with a precise location and trajectory. But the quantum world laughs at such simplistic notions. At this scale, the very idea of a particle as a distinct localized object begins to dissolve. This is the heart of what we call wave-particle duality, one of the most foundational and counterintuitive concepts in quantum physics. It tells us that these fundamental entities don't behave exclusively as particles or as waves. They exhibit characteristics of both, depending on how we observe them. Think about a wave in water. It's not a single point. It's a disturbance, spread out over space with peaks and troughs. Or consider a sound wave. It's a vibration, a pattern of pressure changes, not a distinct object. Now try to apply that to an electron. An electron, like light, can behave like a wave. But what exactly is waving? It's not a physical medium like water or air. In the quantum realm, what's waving is something far more abstract. It's a probability wave. This probability wave describes all the possible locations and states a particle could be in. It tells us the likelihood of finding the particle at any given point in space or with any particular property. Before we look, before we measure, the particle isn't in one definite place. It's spread out like a ghostly smear of potential, existing in a superposition of all its possible states simultaneously. It's like a blurred photograph that only snaps into focus the moment you choose to view it. Or perhaps like a die spinning in the air, simultaneously showing all 6 numbers until it lands and reveals just one. This sounds utterly absurd, doesn't it? How can something be everywhere at once, or be both a wave and a particle? This isn't just theoretical speculation. It's been repeatedly demonstrated through one of the most famous and mind-bending experiments in scientific history, the double-slit experiment. Let's set the stage. Imagine we have a device that can fire electrons, one at a time. In front of this device, we place a barrier with 2 thin vertical slits. Behind the barrier, we have a detector screen that lights up whenever an electron hits it, recording its arrival point. Now, if electrons were just tiny classical particles like miniature bullets, what would we expect to see? If you fire bullets at a wall with 2 openings, most will hit the wall, but some will go through the slits, creating 2 distinct bands of bullet marks on the screen behind them directly in line with the slits. Simple, right? But what if we were firing waves, like water waves? If you send water waves through 2 slits, they don't just create 2 distinct bands. Instead, the waves emerging from each slit interfere with each other. Where crest meets crest, they reinforce. Where crest meets trough, they cancel out. This creates a characteristic and interference pattern on the screen, a series of alternating bright and dark bands. Think of it like ripples spreading out from 2 points in a pond, overlapping and creating a complex pattern. Now, for the quantum surprise. When scientists performed the double-slit experiment, firing electrons one at a time at the barrier, what did they see on the detector screen? Not two distinct bands as classical particles would produce. Instead, even with electrons arriving individually, an interference pattern began to build up over time. Pause and let that sink in. Each electron, fired one by one, somehow behaves as if it's going through both slits simultaneously and interfering with itself. It's as if a single tennis ball thrown at a wall with two holes somehow splits, passes through both holes, and then recombines and interferes with itself before hitting the back wall. Our common sense screams, impossible, yet this is precisely what the electrons do. They don't choose one slit or the other. They explore all possibilities, existing as a probability wave that passes through both, interfering with its own potential paths. This is already enough to make your head spin, but the story gets even stranger. What if we try to be clever? What if we try to watch which slit each electron goes through? We place a tiny detector right at the slits, designed to tell us definitively whether an electron passes through the left slit or the right slit. Here's the second, even more profound quantum surprise. The moment we try to observe or measure which slit the electron goes through, the interference pattern vanishes. Instead, we get those two distinct bands, just like classical bullets. The electrons suddenly behave like ordinary particles, choosing one slit or the other, as if our act of looking forces them to make up their mind. This is the infamous observer effect, and it's not about consciousness in the mystical sense, but about interaction. Any measurement, any interaction that forces a quantum entity to reveal its particle nature collapses its probability wave. Before observation, the electron exists in a blurry, spread-out state of possibilities, a superposition. It's a wave of potential, simultaneously taking all possible paths, but the moment we interact with it, the moment we try to pin down its location or path, that wave function collapses, and the electron snaps into a definite state, appearing as a particle in a specific location. This isn't just a quirk. It fundamentally redefines what we mean by reality. In our everyday world, objects have definite properties whether we look at them or not. My coffee cup is on my desk whether I'm observing it or not. But at the quantum level, it seems that certain properties of a particle, like its position or momentum, don't exist in a definite state until they are measured. The universe, in a very real sense, seems to be playing a game of cosmic hide-and-seek, refusing to commit to a definite reality until we force its hand. So when we talk about electrons, photons, or any fundamental quantum entity, we're not talking about tiny solid bits of stuff in the classical sense. We're talking about dynamic fields of probability, vibrating packets of energy that can manifest as particles or waves, depending on how they interact with their environment, including our measuring devices. They are, in essence, waves of potential, ghosts of possibility that only solidify into definite forms when observed. This shattering of common sense implies that the objective reality we perceive might not be as objective or as fixed as we assume. The very fabric of existence at its deepest level is fluid, probabilistic, and intimately connected to interaction. It's not a pre-written script, it's more like an improvisational play, constantly being created and defined by the interactions within it. We've explored how the illusion of touch is maintained, how atoms are mostly empty space, and now how the fundamental constituents of that empty space are not solid bits, but waves of probability that only solidify upon observation. Reality, it seems, is far more dynamic, interactive, and less definite than our common sense could ever conceive. But if individual particles can be this weird, what happens when two of them are linked together in a special way? What happens when their fates become intertwined, no matter how far apart they are? Prepare yourself, because in our next chapter, we're going to delve into the truly mind-bending phenomenon of quantum entanglement, where particles can be mysteriously connected across vast distances, defying all classical notions of communication and locality. Get ready for reality to get even stranger. Welcome back to Dreamy Science, where we're pulling back the curtain on the universe's most mind-bending truths, one shattered piece of common sense at a time. In our last chapter, we left you hanging with a truly baffling question. What happens when two particles, like electrons, are linked in a special way, defying distance and classical communication? If a particle can be a wave of probability and only settles into a definite state upon observation, what happens if its fate is tied to another particle, perhaps light years away? Prepare yourselves, because today we're diving headfirst into one of quantum physics' most astonishing and counterintuitive phenomena: quantum entanglement. This isn't just a strange quirk of the subatomic world, it's a profound revelation that challenges our fundamental understanding of reality, locality, and even the very fabric of space and time. Imagine this with me for a moment. You have two coins. They're perfectly ordinary coins, indistinguishable from each other. Now let's say you perform a special quantum ritual, a magical process that links these two coins. You then put one coin in your left hand and the other in your right. Without looking, you give one coin to a friend who lives across the country while you keep the other. Now here's the quantum twist. Before either of you looks at your coin, each coin is in a superposition of both heads and tails simultaneously. Remember that from our last chat. A ghostly smear of potential. But here's the kicker. The two coins are entangled. This means they share a single unified quantum state. If one is heads, the other must be tails. If one is tails, the other must be heads. You just don't know which is which yet. Your friend, thousands of miles away, decides to look at their coin. The instant they observe it, let's say it collapses into heads. What do you immediately know about the coin in your hand? Instantly, without any communication, without any signal travelling across the country, you know your coin must be tails. The moment one coin's state is determined, the other's state is also determined, instantaneously, no matter the distance. This isn't just a cool party trick, this is literally what happens in the quantum realm, and it's why none other than Albert Einstein famously dubbed it spooky action at a distance. He truly hated it. He believed that nothing could travel faster than the speed of light, and this instantaneous correlation seemed to violate that sacred principle. He thought it implied some kind of hidden variable, some secret information pre-programmed into the particles, preventing true randomness or instantaneous communication. But as we'll see, the universe had other plans for his common sense. So let's unpack this spooky action. What exactly is happening here? When two particles become entangled, they become intrinsically linked. They don't just have correlated properties, they share a single unified quantum state. Think of it like a cosmic dance where the partners are so perfectly synchronized that if one twirls left, the other must twirl right, even if they're on opposite sides of the ballroom and can't see each other. Before observation, they exist in a superposition of all possible combined states. For our coins, it's a superposition of heads, tails, and tails, heads simultaneously. The act of measuring one particle forces the entire entangled system to collapse into a definite state. Now, a crucial clarification. Entanglement does not allow for faster-than-light communication. You can't use this phenomenon to send a message to your friend across the country. Why not? Because even though you instantly know the state of your coin, you don't choose what state it collapses into. Your friend's measurement of their coin is random. It could be heads or tails. You only know the outcome of your coin after you've measured it, or after your friend tells you what they saw. The information that my coin is tails only becomes useful after classical communication, like a phone call, confirms what your friend saw. So while the correlation is instantaneous, the transfer of usable information is still bound by the speed of light. But this doesn't make it any less mind-blowing. The fact that the particles are so deeply intertwined, sharing a common fate regardless of the vast distances separating them, tells us something profound about the nature of reality itself. It suggests that reality isn't just a collection of independent things interacting locally in space and time. Instead, there's a deeper, non-local interconnectedness at play. For decades, entanglement remained largely a theoretical curiosity, a thought experiment that vexed the greatest minds. But then came John Bell in the 1960s, who devised a clever mathematical inequality, now known as Bell's theorem. This theorem provided a way to experimentally test whether Einstein's hidden variables or the strange non-locality of quantum mechanics was correct. If hidden variables existed, Bell's inequality would hold true. If quantum mechanics was correct and entanglement was truly non-local, then Bell's inequality would be violated. Enter Alan Aspect and his team in the early 80s. They conducted groundbreaking experiments using entangled photons, particles of light, and measuring their polarization. And what did they find? Time and time again, Bell's inequality was violated. These experiments, and many subsequent increasingly sophisticated ones, have confirmed it beyond a shadow of a doubt. Entanglement is real. The spooky action at a distance is literally happening. This has staggering implications for our common sense understanding of the world. First, it challenges locality. Our everyday experience dictates that an object can only be influenced by its immediate surroundings or by something travelling through space to reach it. If I push a ball, it moves. If I shine a light on it, it reflects. But with entanglement, a measurement performed here can instantaneously affect the state of a particle over there without anything having travelled between them. It's as if the universe is not just a collection of separate pieces, but a single indivisible whole, where distant parts can still be intimately connected. This shatters the notion of a purely local reality. Second, it further obliterates the idea of objective reality existing independently of observation. Remember our coins? Before measurement, neither was definitively heads or tails. They existed in a combined superposition. It was only the act of observation that forced them and their entangled partner into a definite state. This isn't just about knowing something, it's about creating the definite reality through interaction. The properties of entangled particles aren't just unknown to us until we look. They truly don't exist in a definite form until one of them is measured. Think about that for a moment. The very properties of fundamental particles, their spin, their polarization, are not predetermined. They are fluid, probabilistic, and only crystallize into existence through the act of measurement. And when they do, they instantaneously dictate the state of their distant partner. This is a universe where reality isn't just out there, waiting to be discovered, but is actively participating in its own creation through observation and interaction. This profound interconnectedness, this non-local dance, is not just some abstract philosophical concept. It's the bedrock upon which future technologies are being built. Quantum computing, which harnesses the power of superposition and entanglement, promises to solve problems that are currently intractable for even the most powerful supercomputers. Quantum cryptography uses entanglement to create unhackable communication channels. And the dream of quantum teleportation, the transfer of quantum information, not matter, from one location to another, is also rooted in this incredible phenomenon. So where does that leave our common sense? It's probably in a heap on the floor, dazed and confused. We've learnt that matter is mostly empty space that touches an illusion of electromagnetic repulsion, that particles are ghostly probability waves until observed, and now that particles can be so intimately linked that measuring one instantaneously influences another, no matter the distance. This isn't just about small things behaving strangely. It's about the very nature of existence being far stranger, far more interconnected, and far less solid and local than our brains are wired to comprehend. The universe, at its most fundamental level, is not a collection of isolated billiard balls bouncing around. It's an intricate, non-local web of probabilities and instantaneous correlations. It suggests that what we perceive as separate objects might be merely different manifestations of a deeper unified reality. But if reality is so fluid, so dependent on observation, and so interconnected across vast distances, what does that mean for the most fundamental aspects of our experience? What about the very stage upon which all this quantum weirdness plays out, the stage we call our space-time? If particles can be everywhere and nowhere until observed, and if they can instantly influence each other across galaxies, then perhaps our understanding of space and time themselves needs a serious overhaul. Join us next time on Dreamy Science as we explore how quantum physics doesn't just destroy our common sense notions of matter and interaction, but also begins to unravel the very fabric of space-time, hinting at a universe even more extraordinary and interconnected than we can possibly imagine. Get ready for a journey that might just make you question if space and time are truly fundamental, or if they too are emergent properties of a deeper, stranger reality. Welcome back, curious minds, to Dreamy Science, where we continue our journey into the quantum realm, a place where reality itself warps and bends in ways our common sense simply can't grasp. If you've been with us, you know we've already shattered the illusion of solid matter, dismantled the very concept of touch, and stared into the abyss of wave-particle duality, where particles don't even exist definitively until we look at them. Then, in our last chapter, we plunged into the mind-bending world of quantum entanglement, where particles share an instantaneous non-local connection, defying our deepest intuitions about cause, effect, and objective reality. We left you hanging with a question, didn't we? If reality is so fluid, so interconnected, so dependent on observation, what does this mean for our most fundamental frameworks of existence? What about the very stage upon which this quantum drama unfolds? What about space-time itself? Is it truly fundamental, a fixed container for everything, or is it too an emergent property, woven from the same strange quantum threads we've been exploring? Prepare yourselves, because today we're challenging the very fabric of the universe. We're going to explore how quantum physics suggests that space and time, those seemingly unshakable constants of our lives, might be nothing like what we imagine. Let's start by grounding ourselves in what we thought we knew. For over a century, Albert Einstein's general relativity has painted a majestic picture of space-time. In this view, space and time aren't separate entities or just a passive backdrop. They are woven together into a single dynamic fabric. Imagine a vast, invisible trampoline. Massive objects like planets and stars create dimples and curves in this fabric, and what we perceive as gravity is simply the motion of other objects following these curves. It's a beautiful, elegant theory that has stood the test of countless observations, from the bending of starlight around the sun to the detection of gravitational waves. It's the theory that tells us time can slow down near a black hole and that space itself can expand. General relativity describes space-time as continuous, smooth, and infinitely divisible. You can always zoom in further and further, finding smaller and smaller points in space and moments in time. It's like a perfectly smooth, unblemished sheet. But what happens when we try to apply our quantum understanding to this smooth sheet? This is where the universe gets truly bizarre, and where common sense takes a vacation. Quantum mechanics, as we've seen, tells us that everything at the fundamental level is quantized. It comes in discrete packets or units. Energy comes in photons, matter in electrons and quarks. So if everything else is quantized, why should space-time be any different? This is the central dilemma that has plagued physicists for decades. How do you reconcile the smooth, continuous space-time of general relativity with the lumpy, probabilistic, quantized world of quantum mechanics? The answer, many believe, lies in the idea that space-time itself might not be fundamental. It might be emergent. What does emergent mean in this context? Think about a picture on your computer screen. From a distance, it looks like a smooth, continuous image. But if you zoom in close enough, what do you see? Pixels. Tiny, discrete squares of colour. The smooth image emerges from the collective behaviour of countless individual pixels. Similarly, quantum theories of gravity, like loop quantum gravity, propose that space-time at its most fundamental level isn't smooth at all. It's granular. It's pixelated. We're talking about scales so incredibly small that our minds can barely grasp them. The Planck length, approximately 10^35 meters, and the Planck time, about 10^43 seconds. These aren't just arbitrary small numbers, they are the theoretical limits where our current understanding of physics breaks down. Below these scales, space and time are no longer smooth. They become a frothing, chaotic quantum foam. Imagine trying to look at a piece of fabric through an increasingly powerful microscope. At first it looks smooth. Then you start to see individual threads. Then you see the fibres making up those threads. At the Planck scale, space-time is not a smooth sheet, it's a tangled, vibrating network of these fundamental loops, or atoms of space. It's like a tapestry woven from countless invisible vibrating threads, and the smoothness we perceive is just an illusion of scale, much like the solidity of your hand. So if space-time is granular, if it's made of these tiny fundamental units, then what does that mean for our everyday experience? It means that the very notion of a fixed place or a precise moment might dissolve at the deepest level of reality. Just as an electron doesn't have a definite position until observed, perhaps space and time don't have a definite structure until they interact with something. This idea of emergent space-time brings us back full circle to entanglement. Remember how we talked about entanglement being this fundamental non-local connection between particles? What if entanglement isn't just a quirky feature within space-time, but is actually the source of space-time itself? This is where things get truly wild, and it's encapsulated in a mind-bending conjecture known as EPR. Don't worry about the acronyms, just focus on the concept. It proposes a deep, profound equivalence between entanglement, EPR, referring to Einstein, Podolsky, and Rosen, who first described entanglement, and wormholes, ER, referring to Einstein and Rosen, who theorized about these theoretical bridges through space-time. What does this mean in plain English? It suggests that when two particles are entangled, they are not just connected across space-time, they might actually be connected by space-time. Imagine those two entangled electrons separated by light years, instantly influencing each other. Instead of seeing this as an action through space, the ER or EPR conjecture suggests that the entanglement is a tiny quantum wormhole, a connection that literally is the fabric of space-time linking them. This idea turns our understanding of the universe upside down. It means that space-time isn't just a pre-existing stage where quantum particles perform their dance. Instead, space-time itself, with all its distances and durations, might be built from the entanglement of countless quantum bits of information. The universe, in this view, isn't a collection of separate objects moving through a fixed space. It's an intricate, interconnected web of quantum relationships, and what we perceive as space and time are the macroscopic manifestation of these underlying connections. Your common sense screams, "But I feel space. I experience time." And of course you do, just as you feel the solidity of your hand, even though it's mostly empty space. But what if that feeling, that experience, is just a higher level emergent property? What if the distance between your hand and your coffee cup isn't a fundamental void that must be traversed, but rather a measure of the degree of entanglement or lack thereof between the quantum fields that constitute your hand and your coffee cup? Think of it like this. If everything is fundamentally interconnected through entanglement, then space is what tells us how disconnected things appear to be. Time, then, is what tells us how these disconnections and reconnections evolve. The ticking clock, the vast distances between stars, these might not be fundamental realities, but rather sophisticated illusions generated by the collective behavior of quantum entanglement. This perspective also lends weight to another radical idea, the holographic principle. This principle, derived from studies of black holes, suggests that all the information contained within a three-dimensional volume of space can be encoded on a two-dimensional surface that bounds that volume, much like a hologram, where a 3D image is projected from a 2D film. This doesn't mean we live in a literal computer simulation, though some theories flirt with that idea, but rather that our 3D reality, including space-time, might be a projection or an emergent phenomenon from a deeper, simpler two-dimensional quantum reality. Imagine a sophisticated virtual reality game. You, the player, experience a rich three-dimensional world with distances, objects, and the passage of time. But at its core, the game is just code, existing on a two-dimensional server. The holographic principle suggests something similar about our universe. Our familiar 3D space-time, with its perceived depths and durations, might be an elaborate projection from a more fundamental quantum reality existing on a boundary somewhere. This is truly a profound unravelling of everything we take for granted. If space isn't a fixed empty stage, but a dynamic emergent property of quantum entanglement, and if time isn't a universal unidirectional river, but a consequence of these same quantum interactions, then the very foundations of our common sense reality crumble into dust. No longer can we think of ourselves as existing in space and time. Instead, we must consider the possibility that space and time are woven by the quantum fluid threads that make up everything, including us. Our sense of separation, of distinct objects, of cause and effect unfolding sequentially. These are the grand illusions, the magnificent emergent properties of a universe that is fundamentally non-local, interconnected, and constantly being shaped by its own quantum nature. the implications are staggering. If space-time is not fundamental, then concepts like travelling through space or going back in time take on entirely new, almost poetic dimension. It opens up possibilities that are currently beyond our comprehension, hinting at a reality far richer and stranger than any science fiction writer could dream. We've journeyed from the illusion of touch to the non-existence of objective reality, and now we've questioned the very fabric of the universe itself. But if space-time is emergent, if reality is so fluid, where does that leave us? What does it mean for our place in this quantum symphony? And what about the ultimate question? If reality isn't objective until observed, who or what is doing the observing? Join us next time on Dreamy Science as we delve deeper into the philosophical implications of quantum physics and explore the tantalizing, unsettling questions about consciousness and its role in shaping the reality we perceive. We're just getting started on dismantling your common sense, and believe me, the best and strangest is yet to come. Welcome back to Dreamy Science, where we continue our exhilarating journey into the quantum realm, a place where common sense goes to get utterly, gloriously annihilated. We've peered into the void that makes up solid matter, witnessed particles dancing as waves until we dared to look, and even seen the universe tied together by invisible, instantaneous threads of entanglement. We've come to understand that space-time itself might be a grand illusion, a projection from a deeper, more fundamental reality. But as our understanding of the universe has deepened, a question has loomed larger and more unsettling than any other, a question that strikes at the very core of what it means to exist, what it means to be real. It's a question that has haunted physicists and philosophers for nearly a century, and it's one that directly involves you. Yes, you, the listener, your mind, your consciousness. If everything we've discussed so far has made your head spin, prepare yourself, because today we're asking, does reality truly exist without consciousness to observe it? Is the universe out there, fixed and objective, waiting for us to discover it? Or is our very act of perceiving it an active ingredient in its creation? This isn't just a philosophical musing, it's a direct consequence of the quantum mechanics we've been exploring. Remember the double-slit experiment. The electrons, those tiny specks of matter, behave like waves, spreading out and interfering with themselves, creating an interference pattern. But the moment we try to observe which slit they go through, they snap back into behaving like particles, choosing a single path, and the interference pattern vanishes. It's as if the universe itself is holding its breath, waiting for us to make up our minds about what we're looking at. This is the famous observer effect, and it's one of the most fundamental, mind-bending truths of quantum physics. Particles don't just have a definite position or momentum, they exist in a fuzzy cloud of possibilities, a superposition of all potential states, until a measurement is made. Only then does the wave function collapse, and the particle chooses one specific reality. But here's where common sense really starts to unravel. What is a measurement? What is an observer? For decades, this has been known as the measurement problem in quantum mechanics. When we say observation, do we mean a photon hitting a detector? A signal being registered by a computer? A human eye seeing the result? A brain interpreting that signal? Where exactly does the collapse happen? At what point in the chain of events does the universe decide to solidify from a soup of possibilities into a concrete reality? Many physicists, especially those adhering to the pragmatic Copenhagen interpretation, would simply say, don't ask too many questions, the math works and that's enough. They argue that quantum mechanics is just a tool for predicting outcomes, not necessarily a description of an underlying objective reality. But for those of us who yearn to understand the universe at its deepest level, the answer feels profoundly unsatisfying. It leaves a gaping hole in our understanding of existence itself. This is where the idea of consciousness causes collapse enters the arena, a truly radical interpretation that suggests consciousness isn't just a passive witness to reality, but an active participant in shaping it. Let's rewind a bit. Early pioneers of quantum mechanics like John von Neumann and Eugene Wigner grappled with the very problem. Von Neumann, a brilliant mathematician, proposed that the collapse of the wave function ultimately occurs at the interface with consciousness. He suggested that the chain of measurement, particle to detector to nerves to brain, continues until it reaches the conscious mind. It's at this final subjective step that the objective reality is determined. Wigner took this idea even further with his famous thought experiment, Wigner's friend. Imagine your friend is in a sealed lab, performing a quantum experiment, say measuring the spin of an electron. Inside the lab, according to quantum mechanics, the electron exists in a superposition of spin up and spin down until it's measured. Your friend measures it, and let's say they find it spin up. Now, from your perspective, outside the sealed lab, you don't know the result of your friend's measurement. As far as you are concerned, the entire system inside the lab, the electron, the measurement device, and even your friend is in a superposition. Your friend is in a superposition of having measured spin up and having measured spin down. It's not until you open the lab door and ask your friend what they saw that your wave function of the entire lab system collapses. Only then does reality solidify for you. Think about that for a moment. If Wigner's friend experiment is taken to its logical conclusion, it means that reality isn't objective and singular. Your friend's reality inside the lab became definite the moment they observed the electron. But your reality outside the lab remained fuzzy until you observed your friend. Whose reality is the real one? And if your friend then went to tell their friend what happened, would their friend then cause their friend's wave function to collapse? It creates an infinite regress, a cascade of collapsing realities, until you reach the ultimate observer. And for some, that ultimate observer is consciousness itself. This isn't just about a simple observation. It implies that before a conscious mind processes the information, the quantum system, and everything interacting with it, remains in a state of indefinite possibilities. It's a truly mind-bending concept. The universe might literally be waiting for us to look at it before it decides what it is. Now, I know what you might be thinking. Surely this can't be right. The universe existed for billions of years before any consciousness arose. Was it just a blurry, indeterminate mess of possibilities until single-celled organisms, or eventually humans, came along? This is precisely the profound philosophical challenge that the consciousness causes collapse interpretation presents. If consciousness is fundamental to the collapse of the wave function, then what was the universe like before conscious observers existed? Did it exist at all in a definite form? Some proponents suggest that perhaps consciousness isn't limited to biological brains, or that there's a cosmic consciousness that has always been present. Others simply accept the paradox, acknowledging that our current understanding of quantum mechanics points to a reality that is deeply intertwined with observation. It's important to note that the consciousness causes collapse interpretation is just one way to grapple with the measurement problem, albeit a deeply provocative one. There are other interpretations, like the many worlds interpretation, which suggests that every time a quantum measurement is made, the universe simply splits into multiple parallel universes, one for each possible outcome. In this view, no collapse actually happens. All possibilities are realized in different branches of reality, thus sidestepping the need for consciousness to collapse anything. But even the many worlds interpretation forces us to confront a reality far stranger than our common sense can comfortably grasp. However, the idea that our observation, our attention, can influence reality isn't entirely without experimental support beyond the basic double-slit setup. Consider the quantum Zeno effect. Named after Zeno's paradox of the arrow, this effect demonstrates that if you continuously observe a quantum system, you can actually prevent it from changing its state. Imagine an unstable atom that is expected to decay at a certain rate. If you continuously measure that atom to see if it has decayed, the act of repeated observation can actually freeze its evolution, significantly slowing down or even preventing its decay. It's like trying to watch a pot boil, but your constant peaking prevents it from ever getting hot. The continuous measurement prevents the wave function from evolving and collapsing into a decayed state. It essentially forces the system to remain in its initial state. This isn't just theoretical, it's been demonstrated in experiments with supercooled ions. The quantum Zeno effect further reinforces the extraordinary power of observation in the quantum world. It's not just a passive act of seeing what's there, it's an active intervention that can profoundly alter the very evolution of a system. So where does this leave our common sense? Utterly bewildered, I imagine. We've moved from the illusion of solidity to the idea that our very presence, our very act of conscious observation might be a fundamental ingredient in baking the cake of reality. The universe, according to this interpretation, is not a grand objective stage upon which we merely play our parts. Instead, it's a dynamic participatory drama where our consciousness might be one of the lead actors, actively shaping the scenery, the props, and even the plot. Our shared reality, then, could be a collective consensus, a symphony of conscious minds agreeing upon what exists. This journey through quantum physics isn't just about understanding tiny particles. It's about fundamentally redefining our place in the cosmos. It challenges us to reconsider the most basic assumptions we hold about reality, about matter, about time, and now about consciousness itself. The boundaries between the observer and the observed, between mind and matter, become incredibly blurred. What if the universe isn't out there waiting to be discovered, but rather in here, a product of our interaction with the quantum field? What if the empty space we talked about in Chapter 1 isn't truly empty, but a sea of possibilities waiting for a conscious mind to give them form? These are not easy questions, and quantum mechanics, while incredibly successful at predicting experimental outcomes, offers no definitive answer to the measurement problem that satisfies everyone. But it forces us to confront the possibility that reality, as we perceive it, is far more subjective, far more fluid, and far more dependent on us than we ever dared to imagine. As we continue to explore the fascinating world of scientific wonder here at Dreamy Science, we'll see how these profound insights into the nature of reality push the boundaries of human knowledge and force us to ask even bigger questions. Next time, we'll delve into the very nature of information itself and how it might be the most fundamental building block of the universe, potentially giving us a new lens through which to view the mysteries of consciousness and reality. Until then, keep questioning, keep wondering, and remember, your common sense is probably still reeling, and that's exactly where it should be. We've peeled back so many layers of what we thought was real, haven't we? From the illusion of touch and the vast emptiness within matter, to particles dancing between possibilities until we look, to the spooky entanglement that threads the universe, and even the mind-bending idea that space-time itself might be a projection. And in our last chapter, we grappled with the truly radical notion that consciousness might be the ultimate ingredient, solidifying reality from a quantum mist of probabilities. It's a lot to take in, I know. Each step has chipped away at our common sense understanding, leaving us with the universe far stranger and more dynamic than we ever imagined. But what if the very stuff of reality isn't stuff at all? What if, at its most fundamental level, the universe isn't made of particles or fields, but something even more abstract, more ephemeral, yet undeniably real? This is where dreamy science invites you to consider perhaps the most profound paradigm shift yet, the idea that information is the fundamental building block of the universe. Imagine for a moment that everything around you, the chair you're sitting on, the air you breathe, the thoughts swirling in your mind, isn't just a collection of atoms, but a vast, intricate pattern of data. Not data about something, but data itself. This isn't just a philosophical musing, it's a concept gaining serious traction in the deepest realms of theoretical physics, suggesting that the physical world we perceive might simply be a manifestation of underlying information. The late great physicist John Wheeler, a pioneer in general relativity and quantum gravity, famously coined the phrase, "it from bit." What he meant was that every it, every particle, every field, every law of physics, even space-time itself, ultimately derives its existence and meaning from bits of information. Think of a bit as the most basic unit of information, a simple yes or no, a 0 or a 1. Wheeler proposed that the universe is fundamentally a gigantic information processor, constantly asking and answering these fundamental questions, and in doing so constructing reality as we know it. It's like thinking about a book. Is the book just paper and ink? Or is it the story, the knowledge, the information encoded within those physical forms? The paper and ink are merely the carriers. The true essence, the profound impact, lies in the information. In the it from bit view, the universe is less like a collection of physical objects and more like an unimaginably vast, self-organizing library of information, with all the physical stuff being the emergent pages and binding. This idea gains incredible traction when we look at the strange behavior of quantum particles. Remember how they exist in a superposition of states until observed? How they carry properties like spin or polarization that are only defined upon measurement. Each of these measurements, each choice the universe makes, each collapse of a wave function, can be viewed as the universe gaining or defining a bit of information. A particle's spin is either up or down, a binary choice, a bit of information. Its location is here or there, another bit. Quantum mechanics, in this light, becomes the science of how information is stored, processed, and revealed. But where does this information live? How is it stored? And what happens to it? For a long time, one of the biggest challenges to this information-centric view of the universe came from the most enigmatic objects in the cosmos: black holes. From a classical perspective, black holes are the ultimate cosmic vacuum cleaners. Anything that crosses their event horizon, the point of no return, is seemingly gone forever, crushed into an infinitely dense singularity. And if something falls in, it takes all its information with it. Its mass, its charge, its angular momentum, these properties remain. But all the intricate details about its constituent particles, their arrangements, their history seem to vanish. This presented a huge problem for quantum mechanics, known as the black hole information paradox. A fundamental tenet of quantum physics is that information can never truly be destroyed. It can be scrambled, transformed, hidden, or spread out, but it can never simply cease to exist. Imagine burning a book. The information isn't gone, it's just encoded in the smoke, the ash, the heat. It would be incredibly difficult, perhaps impossible, to reconstruct the book from that scrambled information, but theoretically it's still there. If black holes truly destroy information, then quantum mechanics, our most successful theory of the very small, is fundamentally flawed. This paradox was a major headache for physicists for decades, particularly for Stephen Hawking, who initially argued that information was lost. But then came the profound realization that black holes aren't entirely black. They slowly evaporate over eons by emitting Hawking radiation, a faint thermal glow of particles. The question then became, does this Hawking radiation carry away the information of everything that fell into the black hole? Or is it just random generic radiation, leaving the information forever trapped or destroyed? The prevailing view now, largely thanks to the work of physicists like Leonard Susskind and Juan Maldacena, is that information is not lost. Instead, it is somehow encoded on the two-dimensional surface of the black hole's event horizon. This is where the holographic principle re-enters our story, but with an even more explicit and mind-bending twist. Think about a hologram. It's a two-dimensional plate that, when illuminated correctly, projects a three-dimensional image. All the information needed to describe the 3D object is actually stored on that 2D surface. The holographic principle, applied to black holes, suggests that all the information about the 3D objects that fell into the black hole is encoded on its 2D event horizon. When the black hole evaporates via Hawking radiation, that radiation slowly carries away the encoded information, preserving it. This is a monumental shift. It means that the seemingly solid three-dimensional reality inside the black hole can be completely described by information living on a two-dimensional boundary. And if this is true for black holes, what if it's true for the entire universe? What if our entire three-dimensional cosmos, with all its galaxies, stars and people, is nothing more than a holographic projection of information encoded on a distant, two-dimensional cosmic horizon? This isn't just a metaphor. It's a serious proposal within quantum gravity, where the universe itself is viewed as a giant hologram, and information is the fundamental currency. If information is indeed the bedrock of existence and the universe is constantly processing these bits, then we naturally arrive at another incredibly provocative concept: the digital universe hypothesis, or what's more commonly known as the simulation hypothesis. If the universe operates like a gigantic information processor, where reality emerges from fundamental bits of data, and where even space-time might be a holographic projection, then the idea that our reality could be a sophisticated simulation, a computational construct, starts to sound less like science fiction and more like a logical, albeit extreme, extension of quantum physics. Think about it. Yes, and the probabilistic nature of quantum mechanics, the way particles only decide on a state when observed or exist as probability waves, could be seen as the universe rendering reality on demand, only generating the specific details that are being actively queried or observed. This is incredibly efficient coding. Why render every blade of grass in a vast landscape if no one is looking at it? The empty space. We've learned that atoms are mostly empty space. From a computational perspective, this is excellent optimization. Why fill up memory with unnecessary stuff if the forces and fields can effectively give the illusion of solidity? Fundamental constants and laws. The very laws of physics that govern our universe, the precise values of constants like the speed of light or Planck's constant, are incredibly fine-tuned for life to exist. In a simulation, these would simply be parameters set by the programmers. Now, I'm not saying dreamy science is definitively claiming we live in a simulation. That's a debate for the ages, and there's no conclusive proof. But what quantum physics does do, especially when we consider the primacy of information, is make the concept of a simulated reality not just plausible, but in some ways elegantly consistent with the deepest mysteries of our universe. It shatters the common sense notion of a physical world that simply is, independently existing with absolute solidity and objective truth. Instead, it offers a vision of a universe that is dynamic, interconnected, and potentially fundamentally informational. So where does this leave our common sense? Utterly demolished, I'd say. We started with touch, moved to particles that are waves, then to connections faster than light, then to space-time as an illusion, then to consciousness as a reality maker, and now to the mind-bending idea that all of it, every single it, is built from bits of information. The universe, according to quantum physics, isn't a collection of tiny solid billiard balls bouncing around in a fixed space and time. It's a symphony of invisible forces, a dance of probabilities, an emergent holographic display, and perhaps at its core, a vast, intricate network of information. This isn't just about understanding the cosmos, it's about understanding ourselves and our place within it. If reality is fundamentally informational, and if consciousness plays a role in observing and thereby solidifying that information, then our role as observers, as conscious beings, becomes incredibly profound. We are not just passive inhabitants, we are active participants in the unfolding informational tapestry of existence. This journey into quantum physics forces us to confront the deepest questions about the nature of reality, pushing the boundaries of what we thought possible. It asks us to let go of our comfortable common sense notions and embrace a universe that is far more wondrous, mysterious, and perhaps even more meaningful than we ever dared to imagine. As we continue to explore, we'll see how these radical insights don't just explain the universe, but profoundly redefine our very understanding of what it means to be real. Welcome back to Dreamy Science, where we're not just bending your mind, we're completely shattering your common sense understanding of reality. If you've been with us on this wild quantum ride, you know we've already questioned everything from the solidity of your own hand to the very fabric of space-time. We've explored how observation shapes reality, how particles can be linked across impossible distances, and how the universe itself might be a holographic projection built from information, perhaps even a simulation. That last thought, the simulation hypothesis, is a profound one, isn't it? It leaves us staring at the stars, wondering if the laws of physics are just lines of code, and if our consciousness is merely a subroutine in a grand cosmic program. It's a concept that takes the idea of reality as illusion to its absolute extreme, suggesting that the very probabilistic nature of quantum mechanics, the vast emptiness of space, and the elegant mathematical precision of our universe could all be signs of an incredibly efficient, self-optimizing computational system. But what does this mean for the fundamental constituents of our simulated, holographic, information-based reality? If everything is ultimately information, what is that information describing? What are the actual bits, or pixels, that make up this incredible cosmic display? We've talked about particles, electrons, photons, quarks, as if they were tiny, discrete objects, little billiard balls zipping around. But quantum physics, in its relentless pursuit of truth, reveals an even deeper, more mind-bending layer to this cosmic onion. This is where we need to introduce you to one of the most elegant and powerful frameworks in modern physics, quantum field theory, or QFT. Prepare yourselves, because QFT takes everything we thought we knew about particles and turns it inside out. making them even less, like common sense objects and more like something out of a dream. Imagine for a moment that the universe isn't made of tiny individual particles at all. Instead, picture it as an immense interconnected ocean of fields, not like a field of grass, but more like a vast invisible medium that permeates everything. For every type of fundamental particle we know, the electron, the photon, the quark, the neutrino, there isn't a particle itself floating around. Instead, there is a corresponding quantum field that stretches throughout the entire universe. Think of it like this. If you have a calm, still ocean, that's like a quantum field at its lowest energy state. When you see a wave on the surface of that ocean, that wave isn't a thing separate from the water. It's an excitation or a ripple in the water itself. In quantum field theory, what we perceive as a particle, and say an electron, is actually just a localized ripple, a vibration, an excitation in the universal electron field. Similarly, a photon, a particle of light, is an excitation in the electromagnetic field. Quarks are excitations in the quark fields, and so on. This is a radical departure from our common sense intuition. We're used to thinking of objects as having definite boundaries, existing independently. But QFT tells us that an electron isn't a tiny, discrete ball. It's a manifestation of an underlying field. It's like trying to grab a wave in the ocean. You can't really hold the wave itself, only the water that makes it up. The wave is a temporary pattern, an energy fluctuation. This perspective profoundly changes how we view the very fabric of existence. It means that what we call empty space is anything but empty. It's not a void. Instead, it's a vibrant, seething tapestry of quantum fields, constantly fluctuating, constantly bubbling with potential. Even in the deepest vacuum, these fields are alive, pulsing with what we call zero-point energy, also vacuum energy. They never truly settle down to absolute stillness, even at absolute zero temperature. There's always a baseline level of quantum jitter, a symphony of invisible forces playing out even when we perceive nothing. And this isn't just a theoretical abstraction, it's incredibly well supported by experimental evidence. The existence of these quantum fields and their excitations explains everything from why all electrons are identical, because they are all excitations of the same electron field, to how particles interact with each other through the exchange of excitations in other fields, like photons mediating the electromagnetic force. Let's revisit some of the mind-bending concepts we've already explored through the lens of QFT. Wave-particle duality? It makes perfect sense now. The wave aspect is the field itself. The probability wave we discussed earlier is a description of the field's potential excitations. The particle aspect is the localized excitation, the ripple, that emerges when we make an observation. It's not that a particle is sometimes a wave and sometimes a particle. It's that the fundamental entity is the field, and what we observe as a particle is a discrete packet of energy or momentum within that field. The field is the ocean, the particle is the wave. Position. If a particle is an excitation in a field, then the field itself can exist in a superposition of states. An electron field can be excited in multiple locations or energy levels simultaneously until an interaction or measurement collapses that distribute excitation into a definite observable particle. The field isn't just excited here or there, it's potentially excited everywhere until pinned down. Entanglement? This also gains a new layer of understanding. When two particles become entangled, it's not two separate billiard balls mysteriously linked. It's two localized excitations within the same quantum field or interacting fields becoming intrinsically correlated. Their underlying field states are linked, meaning that an excitation in one part of the field instantly affects the potential state of an excitation in another part of the field, no matter how far apart they are. The spooky action at a distance is less spooky when you realise that the distance might just be within the same continuous underlying medium. This concept of quantum fields elevates the idea of information as fundamental to a new level. The fields themselves can be thought of as carrying the fundamental information of the universe. Their states, their excitations, their interactions, this is the raw data, the underlying code from which everything else emerges. And this brings us to the ultimate implication: emergence. If everything is fields and their excitations, then the solid objects we perceive, your hand, the chair you're sitting on, the very planet beneath your feet, are not fundamental. They are emergent properties of these underlying quantum fields. They're incredibly complex, stable patterns of excitations and interactions, coalescing into what our macroscopic senses interpret as solidity and form. Think of a hurricane. It's a powerful, distinct entity with a recognizable shape and behavior. But a hurricane isn't a fundamental thing in itself. It's an emergent pattern of air molecules, water vapor, energy and atmospheric forces. The individual molecules aren't hurricanes, but their collective behavior creates one. In the same way, you, I, and everything around us are incredibly intricate, organized emergent patterns arising from the excitations of quantum fields. This is why quantum physics destroys common sense. Common sense tells us the world is made of discrete, solid stuff. Quantum physics tells us it's made of invisible, ubiquitous fields, constantly fluctuating, constantly interacting, giving rise to temporary ripples and vibrations that we interpret as particles. And these particles, in turn, form the emergent structures we call atoms, molecules, and ultimately everything we see and touch. The universe, then, is a symphony of invisible fields vibrating and interacting in ways that create the illusion of matter, energy, space, and time. It's a dance of probabilities and potentials, a cosmic ballet where the dancers are not solid objects but ephemeral excitations in an omnipresent medium. This perspective makes the holographic principle even more compelling. Perhaps the information encoded on a boundary is literally the information about the states and excitations of these fundamental fields, which then project our 3D reality. And the simulation hypothesis gains another layer of plausibility. Perhaps these quantum fields are the most fundamental code or data structures within the simulation, constantly calculating and rendering the emergent reality we experience. This understanding of quantum fields forces us to confront the idea that our reality is far more fluid, interconnected, and fundamentally less solid than we ever imagined. It's a universe of potential constantly collapsing into definite states through interaction and observation, all built upon a foundation of vibrating, omnipresent fields. But if our reality is so ephemeral, so emergent, so tied to these quantum fields, what about the most fundamental emergent property of all? What about time itself? We've already hinted that space-time might be emergent from quantum connections, but what if time as we experience it is also a profoundly different beast at the quantum level, perhaps even an illusion? What if the arrow of time, the relentless march from past to future, is not a fundamental property of the universe, but another grand emergent phenomenon? Join us next time on Dreamy Science as we delve into the quantum nature of time, exploring how this final frontier of common sense is utterly dismantled by the strange and beautiful laws of the quantum realm. Prepare to have your perception of past, present, and future irrevocably altered. Welcome back to Dreamy Science, where we continue our mind-bending journey into the quantum realm, systematically dismantling everything your common sense holds dear. We've unravelled the illusion of solidity, peered into the probabilistic heart of reality, watched particles dance in spooky entanglement, and even glimpsed a universe woven from information emerging from fundamental quantum fields. Now, as you're listening, I want you to take a moment and feel the relentless march of existence, the seconds ticking by, the undeniable progression from past to future. We all experience time as an absolute universal river, flowing ever onward, carrying us from birth to inevitable decay. This linear, unidirectional flow seems to be the very bedrock of our experience. It dictates causality. Cause precedes effect. It gives meaning to memory, to anticipation, to free will. But what if I told you that this fundamental, inescapable aspect of your reality, time itself, might be nothing more than an elaborate illusion? What if at the deepest, most fundamental level of the universe, time doesn't exist at all? This isn't just a philosophical musing. It's a radical implication arising directly from the equations of quantum physics, equations that describe the universe with staggering precision. Let's start with what we think we know about time. Classically, thanks to Newton, time was an absolute, uniform, universal clock, ticking away independently of everything else. Einstein, with his theory of relativity, shattered that notion, showing us that time is relative, intertwined with space to form space-time, and can be warped by gravity and speed. Your time can literally pass differently from mine, depending on our relative motion or proximity to massive objects. But even in Einstein's universe, time still flows, it still moves forward, it still has an arrow. So where does this arrow of time come from? Why do broken eggs never spontaneously reassemble? Why do we remember the past but not the future? At the macroscopic scale, the answer lies in something called entropy. We touched upon it when discussing information, but let's zoom in a bit. The second law of thermodynamics tells us that the total entropy, a measure of disorder or randomness, of an isolated system can only increase over time or stay the same, never decrease. This irreversible increase in disorder is what gives time its direction. It's why a tidy room tends to get messy, not the other way around. It's why processes like aging occur. But here's the kicker. At the fundamental quantum level, the laws of physics are almost entirely time symmetric. This means that if you were to watch a video of a quantum interaction, say two particles colliding and scattering, you wouldn't be able to tell if the video was playing forwards or backward. The equations governing these interactions work perfectly well in either direction. There's no inherent arrow at the microscopic scale. Particles can, in theoretical terms, move backward in time in a Feynman diagram, and the physics still holds. This creates a profound paradox. How does a universe governed by time-symmetric fundamental laws give rise to a macroscopic reality where time relentlessly marches forward, driven by entropy? It's like watching a perfectly reversible ballet performed by individual dancers. But when you zoom out, the entire stage seems to be moving only in one direction. This is where quantum gravity theories, which attempt to reconcile quantum mechanics with general relativity, deliver their most stunning blow to common sense. Many of these theories suggest that time, as we perceive it, is not a fundamental property of the universe but an emergent phenomenon. Just like solidity, just like particles, time itself might emerge from something deeper, something timeless. Perhaps the most famous and unsettling implication comes from the Wheeler-DeWitt equation. Developed by quantum pioneers John Wheeler and Bryce DeWitt in the 1960s, this equation is an attempt to describe the quantum state of the entire universe. It's a foundational equation in quantum cosmology, trying to combine quantum mechanics with general relativity. And when you look at this equation, something incredible, something truly mind-bending happens. The variable for time vanishes. Think about that for a moment. An equation that describes the wave function of the entire cosmos. All its matter, energy and space-time doesn't have time in it. It implies that at the ultimate quantum level the universe is static, a timeless entity. There is no evolution, no beginning, no end, no flow. It's just being. How can we possibly reconcile this with our lived experience? If the Wheeler-DeWitt equation is correct, then the universe at its most fundamental is like a vast, unchanging snapshot, an eternal now. Our perception of time passing, of a sequence of moments, would be an illusion, a trick of our minds or an emergent property of the universe's complex dynamics. Imagine a block of marble. Within it, an artist carves a statue. From the perspective of the marble block itself, the statue always is. It's merely a configuration within its timeless existence. Our perception, however, is of the artist's process, the carving over time. The Wheeler-DeWitt equation suggests the universe is the marble block, and our experience is the carving. This concept leads us directly to what's known as the block universe, or eternalism. In this view, past, present and future are not transient moments, but are all equally real and exist simultaneously, like frames in a cosmic film reel. We simply experience them sequentially, much like flipping through the pages of a book, believing only the page we're currently reading truly exists. But from an external, timeless perspective, every page, every moment is already there. This view shatters our common-sense notions of causality. If all moments already exist, then the future isn't something that will happen. It's something that is, just not experienced by us. Yet, this doesn't mean fate is predetermined in a classical sense, but it fundamentally redefines what happening even means. So if time isn't fundamental, how does it emerge? One leading hypothesis suggests that time emerges from quantum entanglement. We've seen how entanglement links particles across space, creating a unified quantum state. What if entanglement also links different moments or configurations of the universe? Imagine the universe as a gigantic, intricate quantum computer constantly processing information. Our experience of time could be akin to the sequential processing of data, or the way our consciousness reads different quantum states as they become entangled and decohere. The arrow of time then might not be a cosmic clock, but an arrow of increasing entanglement or the accumulation of correlations within the universe. As quantum systems interact and become more and more entangled, they lose their individual quantum purity and settle into a more definite classical-like state. This process, often linked to the emergence of classical reality, could be what we perceive as the forward march of time. Another perspective links the emergence of time to the observer effect and the measurement problem we discussed earlier. If observation collapses the wave function, bringing a probabilistic reality into a definite state, perhaps our very act of observing and interacting with the universe is what creates the flow of time. Each measurement, each interaction, could be seen as a step forward in an ever-unfolding narrative that we ourselves are constructing through our conscious engagement with reality. This is not to say that time is only in your head. It's more profound than that. It's suggesting that the universe, at its deepest level, is a timeless quantum state, and our experience of change, of past, present, and future, is an emergent property of how that timeless state manifests itself to conscious observers, or how its internal correlations evolve. This idea resonates with the concept of space-time itself being emergent, as explored in Chapter 4. If space and time are not fundamental but arise from the underlying quantum fabric, perhaps from entanglement, then the Wheeler-DeWitt equation's timelessness makes perfect sense. The universe is not in space-time. Space-time is an emergent property of the universe's quantum state. The implications of a timeless universe are staggering. If time isn't fundamental, then our deepest intuitions about cause and effect, about memory, about anticipation, and even about free will are built upon a cosmic illusion. If the future already exists, what does that mean for the choices you make right now? Are they truly choices, or are they simply the unfolding of a pre-existing configuration? Quantum physics isn't just challenging your common sense about what things are, it's challenging your common sense about when things happen. It's suggesting that the very framework of before and after, of beginning and end, is a construct, a useful fiction that allows us to navigate a much stranger, much more profound reality. We've stripped away solidity, replaced particles with probability waves, found spooky connections across vast distances, dissolved space-time into a quantum foam, and now we're being asked to consider a universe where time itself is an illusion. Your journey through the quantum world is a journey into a reality so alien, so counterintuitive that it forces you to question everything you've ever taken for granted. So that as we continue to unravel the universe's deepest secrets, prepare to confront the ultimate challenge to your perception. If time isn't real, what then is? What governs the unfolding of events, if not a universal clock? And what does this mean for our place within this timeless, entangled cosmos? The answers, as always, are far stranger and more beautiful than common sense could ever imagine. Last time we dared to gaze into the abyss of time itself, questioning its very existence as a fundamental aspect of our universe. We explored how, at the deepest quantum levels, the laws seem utterly indifferent to the forward march we perceive, suggesting that our experience of linear time might be nothing more than an emergent illusion, a trick of consciousness, a byproduct of entanglement, or perhaps just a local phenomenon within a timeless static block universe where past, present and future all simply are. If that wasn't enough to send your common sense reeling, if the idea of a universe where every moment exists simultaneously didn't completely unravel your everyday understanding of cause and effect, then prepare yourself. Because quantum mechanics has another, even more audacious interpretation of reality waiting in the wings, one that doesn't just challenge our perception of time, but shatters the very notion of a single reality itself. We're talking about a concept so profound, so utterly mind-bending, that it makes the idea of a timeless universe feel almost conventional. We're about to dive into the many worlds interpretation, and trust us, it's going to make you question every decision you've ever made, every path you've ever chosen, and every outcome you've ever witnessed. Remember our friend, the quantum wave function, that mathematical description of all possible states a particle could be in before we observe it. We've learned that in the standard Copenhagen interpretation, the act of observation collapses this wave function, forcing the particle to choose a single definite state from its myriad possibilities. This measurement problem has been the bane of physicists for decades, leading to all sorts of philosophical conundrums, including the disturbing implication that consciousness might play a role in shaping reality. But what if there's another way? What if the wave function never collapses? What if instead of choosing one outcome, the universe simply splits? This is the radical yet surprisingly elegant proposition put forth by Hugh Everett III in the late 1950s. The many worlds interpretation, MWI, posits that every time a quantum measurement is made, every time a particle interacts, every time a choice is presented at the quantum level, the universe doesn't settle on a single outcome. Instead, it branches, splitting into a multitude of parallel universes, each representing a different possible outcome of that quantum event. Let that sink in for a moment. Imagine a single quantum particle existing in a superposition of spin up and spin down. When you measure its spin, your common sense dictates you'll find it either spin up or spin down. But MWI says, no. In one universe, you measure spin up. In another equally real universe, you measure spin down. Both outcomes occur just in different, non-interacting realities. This isn't just about particles, this is about everything. Every quantum interaction, every photon hitting your retina, every electron moving through your brain, every single probabilistic event, and the universe is absolutely brimming with them, causes a branching. Think about it this way. You're standing at a crossroads. In your common sense world, you choose left or right, and the other path simply doesn't exist for you. But in the many world scenario, when you make that choice, the universe branches. There's a you who goes left, experiencing that reality, and there's an equally real you who goes right, experiencing that separate reality. Both paths are taken, both outcomes are realized, just in different branches of an ever-expanding cosmic tree. This is where the famous Schrödinger's cat thought experiment gets a truly bizarre resolution. Remember the cat in the box, simultaneously dead and alive until you open it? In MWI, when the Geiger counter either detects decay or doesn't, the universe splits. In one universe, the atom decayed, the poison was released, and the cat is dead. In another identical universe, the atom didn't decay, the poison wasn't released, and the cat is alive. When you open the box, you also split. One version of you sees a dead cat, another version of you sees an alive cat. Neither of you experiences the other's reality, yet both are equally real. Your common sense screams, but I only experience one reality, I only see one outcome. And that's the trick. The you that exists in one branch of the universe is completely unaware of the you in the other branches. You experience a continuous singular reality because your consciousness is part of that branching process. You, as a collection of quantum particles, are entangled with your specific branch of the universe, unable to perceive the others. It's like being on a train track that constantly forks. You only ever see the track you're on, even as countless other trains speed off on parallel paths. The implications of this are staggering. If MWI is correct, then every single possibility allowed by quantum mechanics is realized somewhere, in some universe. Every quantum fluctuation, every roll of a quantum die, every tiny probabilistic event that could have gone one way but went another in your universe, all those other possibilities are playing out right now in parallel universes that are constantly being created. This means that the universe isn't just big, it's infinitely vast, constantly expanding not just in space but in branching realities. Every decision you make, every coin toss, every random event potentially creates a new set of parallel universes. There's a universe where you chose a different career, a universe where you married a different person, a universe where you said that one thing you regret, and a universe where you didn't. There's a universe where dinosaurs never went extinct, a universe where humanity never evolved, a universe where gravity works differently. Anything that is quantum mechanically possible is happening. This doesn't just destroy your common sense notion of a single objective reality, it obliterates it entirely. The world you perceive, the timeline you inhabit, the choices you remember making, these are just one sliver of an unimaginably vast branching multiverse. It means that the measurement problem isn't solved by wave function collapse, but by the universe simply realizing all outcomes, distributing them across an ever-growing tree of realities. From the perspective of dreamy science, this is perhaps the ultimate challenge to our ingrained perceptions. We've talked about how solidity is an illusion, how touch is an illusion, how particles are waves, how observation shapes reality, how time itself might be an illusion. Now, we're confronting the idea that the very reality we inhabit is just one of countless others, constantly splitting, constantly diverging. It's an incredibly elegant solution to some of quantum physics' deepest mysteries, avoiding the need for a mysterious collapse mechanism or the spooky action of consciousness directly influencing outcomes. But it comes at a cost that our common sense finds almost impossible to bear. The existence of an infinite number of yous living out an infinite number of possible lives. The beauty and terror of MWI lie in its radical simplicity and its profound implications. If every quantum possibility is realized, then in a very real sense, all outcomes already exist. Our experience of choosing a path, of observing a single outcome, is merely our consciousness following one specific branch of this ever-diverging reality. It challenges our understanding of identity, free will, and even the very meaning of existence itself. Are you truly making a choice, or are you simply following a predetermined path within one of many pre-existing branches? This interpretation, while not universally accepted, is gaining traction among physicists because of its mathematical consistency and its ability to resolve the measurement problem without introducing arbitrary external mechanisms. It suggests that the quantum weirdness we observe isn't just a quirk of tiny particles, but the fundamental nature of reality itself, playing out on a grand cosmic scale. So as you go about your day, making choices, interacting with the world, remember this: your common sense tells you there's only one you and one reality. Quantum physics, through the lens of the many worlds interpretation, suggests that every moment is a branching point, and countless versions of you are experiencing countless other realities, utterly oblivious to one another. We started this journey by realizing you're not really touching anything. We then discovered that everything is mostly empty space, and particles are simultaneously waves. We learned that observation might create reality, and that time itself might be an illusion. Now we're faced with the idea that all possible realities are unfolding simultaneously right alongside yours. What does it even mean to be real when reality itself is an infinite, branching fractal? What does it mean to be you when countless versions of you exist? These aren't just philosophical musings, these are the profound, disorienting questions that quantum physics forces us to confront. As we continue to navigate this landscape where common sense goes to die, we must ask ourselves, if reality is this fragmented, this fluid, this utterly mind-bending, what else could be lurking in the quantum shadows, waiting to dismantle our most fundamental assumptions? What's left to discover when the very fabric of existence is so radically different from what we perceive? Join us next time as we continue our exploration into the deepest, most unsettling truths of the universe. Welcome back to Dreamy Science, where we continue our journey into the quantum realm, systematically dismantling everything your common sense holds dear. In our last exploration, we left you teetering on the edge of an abyss, staring into the infinite possibilities of the many worlds interpretation. We dropped a bombshell that might have left you wondering if your own reality, your own choices, even your own identity are truly as singular as you've always believed. Today, we're not just going to peek into that abyss. We're going to dive headfirst. We're going to explore what it truly means if every quantum event, every flicker of uncertainty, doesn't just resolve into one outcome, but instead causes the entire universe, and you along with it, to branch into myriad parallel realities. Remember, the core problem MWI seeks to solve is the infamous measurement problem. If the universe is fundamentally described by a wave function that exists in a superposition of all possible states, why do we only ever observe one definite outcome? Why does the cat in Schrödinger's box appear either alive or dead, never both, when we open it? The Copenhagen interpretation, which we discussed earlier, simply says the wave function collapses upon observation, but it doesn't tell us how or what constitutes an observation. It's a bit like saying magic happens here and then moving on. The many worlds interpretation, proposed by Hugh Everett III in 1957, offers a radically different, and some would argue, far more elegant solution. The wave function never collapses. Instead, every time a quantum measurement is made, or really, every time there's an interaction that causes quantum possibilities to diverge, the universe simply splits into a multitude of parallel realities. Each reality represents a different possible outcome of that quantum event. Think about that for a moment. You just flipped a coin. In your reality, it landed heads. But according to MWI, at the precise moment the coin's quantum state interacted with the air, the table, and ultimately your eyes, the universe branched. In one branch it landed heads. In another, equally real branch, it landed tails. And in countless other branches, it might have spun forever or vanished, if those were quantum possibilities. Every single quantum interaction, happening billions of times a second all around us, is a branching point. This isn't just a philosophical quirk, it's a profound shift in our understanding of existence. It means that every decision you make, every choice, every random quantum fluctuation within your brain or your environment is not leading you down a single predetermined path, but rather causing you to split, to experience all possible paths simultaneously, albeit in separate non-communicating realities. Let's tackle the most unsettling implication first: your identity. If you're listening to this podcast right now, and you choose to raise your hand, which please do, I'd love it if you did. In one universe, your hand goes up. In another, it stays down. Which you is the real you? The answer, according to MWI, is both. And all the other yous who made different choices or experienced different quantum outcomes. It's like a cosmic choose-your-own-adventure book where you simultaneously read every single possible ending. This shatters the common-sense notion of a singular, continuous self. You're not just one person, you're an ever-branching tree of selves, each experiencing a unique sequence of quantum events and choices. The you that is listening to this right now is just one of an unfathomable number of yous traversing a particular branch of this cosmic tree. But if this is true, why don't we perceive these other branches? Why do we experience a single coherent reality? This is where the concept of decoherence comes in. As these branches diverge, they quickly become decoherent. Imagine waves in a pond. If two waves interfere, they create a new combined pattern. But if they move away from each other and never interact again, they become effectively separate. In the quantum realm, once these worlds branch, the quantum states that define them become orthogonal, meaning they can no longer interfere with each other. From your perspective within one branch, the other branches become effectively invisible, inaccessible, and entirely separate. It's like trying to tune into two different radio stations on the same frequency. Impossible. Each branch is a distinct frequency of reality, so while it's not that new universes are being created out of nothing in some wasteful cosmic explosion, rather, the single universal wave function that describes everything is simply evolving, and we, as observers, are embedded within one of its many possible configurations. The splitting isn't a violent rupture, but a continuous subtle divergence of states. Another big question that often arises with MWI is, what about probability? If all outcomes happen, does probability lose all meaning? If you roll a dice and a 6 comes up only 1/6 of the time, how does that make sense if in some universe every roll results in a 6? This is one of the most debated aspects of MWI. Proponents argue that while all outcomes exist, the measure or weight of the branches corresponds to the probabilities we observe. So while a 6 will occur in some branch, the branches where a 1, 2, 3, 4 or 5 occur are collectively more numerous or thicker in some abstract sense, leading to the statistical regularities we experience. It's not that you're guaranteed to see a 6 if you look hard enough across the multiverse. It's that the subjective experience of probability still holds true within your particular branch. The elegance of MWI lies in its simplicity. It takes quantum mechanics at face value. It says, if the equations say all possibilities exist, then all possibilities do exist. No mysterious collapse, no hidden variables, just a straightforward application of the Schrödinger equation to the entire universe. It suggests that our universe isn't just one story, it's an infinite library, with every possible version of every story being written simultaneously. This perspective is both liberating and terrifying. Liberating because it means every possibility you can imagine is real, somewhere. Terrifying because it means every mistake, every missed opportunity, every tragedy also plays out in countless other realities. It fundamentally challenges our sense of control and agency. If all outcomes of your choices are realized, does free will truly mean what we think it does? Or are we simply along for the ride, our consciousness surfing one specific wave in an ocean of infinite possibilities? The many worlds interpretation is, without a doubt, one of the most audacious and mind-bending ideas to emerge from quantum physics. It takes the quantum weirdness we've been discussing, superposition, non-locality, and extrapolates it to the grandest scale imaginable, suggesting that our entire perceived reality is just one thread in an infinitely complex, branching tapestry. It completely demolishes the common-sense idea of a single objective shared reality, replacing it with a constantly diverging subjective experience across an ever-expanding multiverse. It's a view of the universe that demands we reconsider everything we thought we knew about ourselves, our choices, and the very nature of existence. It's a powerful reminder that the universe doesn't care about our common sense, it simply is. And the more we peel back the layers of quantum reality, the more we find ourselves in a cosmos far stranger, far more intricate, and far more awe-inspiring than any of our intuitive notions could ever have conceived. As we stand here, gazing into the infinite branches of the multiverse, we've explored how quantum physics has systematically dismantled solidity, locality, objectivity, linearity, and now even the singularity of our reality and identity. But what does it all mean? How do we reconcile these seemingly contradictory truths? And what might be the ultimate underlying fabric from which all these quantum wonders emerge? Join us next time on Dreamy Science as we continue our quest to understand the universe, one shattered common-sense notion at a time. We'll delve deeper into the philosophical implications of these quantum revelations, asking the ultimate questions about consciousness, meaning, and the very nature of reality itself. You won't want to miss it.